my talk is like similar in spirit as the first talk. There will also be a tiny amount of overlap because we were researching the same type of topics. The main difference is that in my analysis, so basically in the last 3 years or so, we were exploring all these dependency issues we are facing, but at the level of different programming language package distributions, for JavaScript, for Cargo, so we have like maybe 7 different package distributions, and basically what we wanted to learn and to understand is whether the same type of dependency issues are actually being faced to a larger or smaller extent in the different packaging ecosystems. So everything we did was basically only by looking at the package metadata, so we didn't actually dive into the source code, the static code analysis, or dynamic code analysis, because at this scale it's not really feasible at all. All of this research is also part of another project, the FOSDEM project. It's basically a project that is more or less going on parallel. It's called Assisted for different project universities. The talk will basically, so if you want to read much more details, it's based on 5 presentations that we have published different articles and conferences and journals. So, okay, you have already heard from Lucius that there is lots of different dependency issues. This is basically a repetition. One of the problems is what actually we coin as technical lag. Basically, you have outdated dependencies, and because of this, you are missing opportunities to have new functionality, you are missing opportunities to benefit from bug fixes or security vulnerabilities. On the other hand, maybe you don't want to update because it's too costly, it takes too much effort. We also heard in the previous talks the notion of dependency hell. Basically, you might have too many direct dependencies, and even worse, too many indirect translate dependencies, and this, as we will see later, this translate dependency graph can be really, really high. So high that it's actually not even manageable to start looking at all of what's happening in all of your translate dependencies. Another problem is that you might have, if you actually decide to upgrade, you might have broken dependencies, backward incompatibilities. Sometimes you might have different dependencies that you cannot install together, which is again another problem. Some of the reasons of these dependency issues are actually more social in spirit, because maybe these, we depend on a package that's not updated. Why? Because basically there is no maintenance anymore for this package. And then there's other problems that, I think it was also Roger that mentioned it, for example, you might have license problems, and also it's not always clear what are the update policies of all the packages that you're depending on. So basically quite a different number of things. For some of these things there is tooling available, for example for the licensing, there's probably many more tools, but I'm just mentioning one, the TimeLift, which is not open source as far as I know, has this for detecting whether you have license problems. The transitive dependency problem is already mentioned in the 2 previous talks, so I would not go as far as saying that it broke the entire internet. That would be like a little exaggeration, but actually it is indeed a quite huge problem. If actually we start to count what was the actual effect of the NPM incident on only the NPM ecosystem, so only all the NPM packages that were existing at that moment in the NPM dependency graph, then basically this was, it had an impact locally in all the NPM libraries, as 5,400 packages were directly or indirectly affected by this single package. Of course, all of these packages were also used by external clients, by websites, and there, of course, the impact was much more huge. But inside the ecosystem itself, it was 5,400 packages, which is pretty big. This corresponds to about 2% of all the packages at that time in the ecosystem. There's a similar incident that was much earlier on. This was, for example, for the, which one is this? Sorry, I forgot the logo. This is
RubyGems.
RubyGems, yeah, right, of course, actually. In that case, there was one package that was used by another package that was massively used. In that case, it was a similar problem that broke 5% of all the packages. So basically, what you think is needed is like tools that also help you to assess if you have a particular package that is transitively dependent upon downstream. What would be the possible impact that any change, any breaking problem, any security vulnerability might have on the rest of your ecosystem. So I will present in the next slides some analysis. Basically, to get all of the data for the different ecosystems we were studying, we were basically using the libraries.io dependency management service. They have lots of data, metadata for all packages, all dependencies, all releases over time for all of these different package managers. So of course we didn't study all of them, there's a little bit too much, and also we only wanted to study those for which we found that the package dependency metadata was sufficiently precise. So we actually manually checked because for some of them, like for Maven and for Phi, it was not reliable to use this data, but for the others we did some checking to find out whether it was okay. So as a first study, we actually looked at 7 different package managers for 7 different programming languages. You can see that most of them are dynamic, interpreted or compiled programming languages. Some of them are pretty old, so starting from, so we have CPAN and CRAN in the 90s. Some of them are pretty new, like Cargo, only created in 2014. Also in terms of number of packages that were available, so in this case it really was known, this was the oldest study in April 2017. We should maybe do it again today to see what has changed. But it can, in that case, it ranged from 9,000 packages for Cargo to 460,000 packages for NPM. Today it's already more than 1,200,000 packages, I think, for NPM. I didn't check. For dependencies, it's even much more, like 13 million dependencies, so it was quite a challenge to run the analysis. So the first thing we experienced was, if you look at the evolution over time, how fast are these different ecosystems growing? So we looked at the growth in terms of number of packages, number of dependencies. You can see the growth here. It looks like okay growth, except that this is an exponential, logarithmic scale. So in most of the cases, we found exponential growth in terms of number of packages, in terms of number of dependencies. And like the worst student in the class was NPM, which is actually growing much faster than the others. And actually here you can see this basically is an order of magnitude difference now, now, in 2017 between NPM and the others. Cargo as well, it was very small because it was just born in somewhere in 2014. It's growing much faster. It's actually, now it's already higher than the lowest one here. So it's interesting to see how this will continue to evolve over time. That's basically just the growth, so we have an exponential growth in the size of these package dependency networks, which of course makes the analysis also more challenging over time, especially if you want to explore these constant dependency networks. For a number of updates, we also checked how frequently are packages being released, how many new package updates you have for existing packages, and basically there we saw that like for half of the different packages, there is an update within every 2 months on average, so that's quite frequently. And the younger a package is, or the more dependence a package has, the more packages relying on this package, the more frequently it will be updated. Then another thing we try to analyze is the type of network that is being formed. Basically, these types of dependency networks, they form a kind of complex network. Basically, we find evidence of this overall behavior everywhere. I think so. For example, there is a minor, like a small set of packages that actually, how to call it, receive all incoming dependencies. Like 20% of all required packages cover 80% of all the incoming dependencies. Oh, it was not on. Now I start all over again. We'll skip this slide. One thing we wanted to know, so we already mentioned before, we have this problem of transitive dependencies in the different packaging in the different package dependency graphs. One of the things we wanted to know is, can we actually measure this potential transitive impact that a change in a single package may have on all the other packages in the ecosystem? So, if you remember one of the previous slides for NPM, the impact of left cut was 5% of all packages within the ecosystem at that time were affected. For the other example, it was 2% for NPM left cut and 5% for the active record in Ruby gems. So basically here, what we try to measure is, say we focus on 5% and we start counting over time how many packages at a particular point in time will, if they break, affect at least 5% of all the other packages in the ecosystem. And then we can count how many packages these are. Here we see the case for NPM. So it's growing over time, it's growing faster than the others. Like in 2016, there were more than almost 250 packages that had an impact of at least 5% of the entire ecosystem. Until somewhere in March 2016, what's happening here, that's basically the left path incident, and then it's going down a little bit, and then stabilizing again. So they apparently learned from their mistakes, it's going down, then it's again stabilizing. I don't know what happens now, is it still going up? I hope it's not going up too faster, but it's still like 200 magnitude higher than all the others. I'm interested to find out what will happen for cargo, because there we also see that it started very low and it's now becoming the second one. So maybe this is also a problem for cargo as well in terms of transitive dependencies. What we try to explore is, okay, why is this happening? What is actually going on? So we are looking at the transitive dependency depth. In that case, it was impossible, because of computing resources, to do this for all possible packages in the ecosystem. So we only looked at the top level packages, which is those packages that don't have any incoming dependencies from within the same package manager. They might have of course clients, but not within the same, not other libraries that depend on it. In that case, basically what we can see is that here for example, if take cargo, the dependency depth for more than 50% of all packages, they have a dependency depth of at least 6 or more. So this means a dependency of dependency of dependency of dependency of dependency of dependency, and so on. This is really the worst case cargo. Lots of very deep level of transitive dependencies. For NPM, it's also quite high. You can see it here. The other systems are a little bit more well behaved. NuGet, which is for .NET, is also a bit problematic because of this. So depending on which ecosystem you take, some might be problematic. Cargo, NPM, and maybe NuGet. Others like C10 and C1, they are much more well behaved. So then we have the problem of outdated dependencies, which I already mentioned before. What should you do? Should you upgrade to the newest version so that you can benefit from bug fixes, security fixes, benefit from new features? Or should you keep to your old version because it's easier for you, but and because you don't want to introduce breaking changes, but you might have vulnerable packages in that case? It's difficult to say. What we actually also try to analyze, in this case for NPM, is to find out to which extent the fact of being outdated, of a package being outdated, depends on which dependency constraints you're using in your packages. So basically you can use scalar constraints, strict constraints, tilde constraints, and here you can see it in different colors. Basically I think the interesting one is the strict constraints. You can see that about 1 out of 3 packages is specifying strict constraints in their dependencies, which basically means that it's not possible to benefit from minor upgrades or patch upgrades of your dependencies, except if you manually each time modify your dependency yourself. So this is a pretty high percentage. That might be one of the reasons why you have lots of outdated packages in NPM. So to actually, so one of the things we are currently doing is proposing this new measurement framework, which is called technical act, is a way to decide to measure to which extent a package can be outdated because it has outdated dependencies. So I will maybe give an example of this. Suppose I have this package, which is one of the packages in NPM, that has 3 direct dependencies and 1 indirect dependency with lots of different dependency constraints, a strict constraint here, error constraints here, a tilde constraint here. And because of the constraints, this particular version can only depend on the version with respect to this constraint, so 2.7.0, so it's missing 3 versions. So because of this, it's outdated with, well, you can actually compute the outdatedness in terms of time. If the outdatedness here will be 4 days, because the most recent version is 4 days younger than this one. For this version, which is an indirect dependency, you're outdated with, how much is this? More difficult to see, like 6 months or so. So transitively, you are updated with 6 months for direct dependencies only 4 days. So if you would only look at the transitive dependencies, it's okay. If you would only look at the direct dependencies, it's okay. If you also look at the indirect ones, it's much more problematic. This is, well, in that case, you can measure if you are outdated in terms of time. You could also do this in terms of number of versions you are behind, but you could actually do the same for bugs to find out how well would I be if I upgrade in terms of could I reduce the number of bugs in my current component because my dependencies have bugs, or could I reduce the number of vulnerabilities? If you want to know more about this, I presented the technical lag framework yesterday in the ChaosCon conference, which I think there's also a video about it, not yet, but it will be available soon. There's only, to some extent, some tools are starting to also provide similar support. For example, if you know the dependency manager David for NPM, it provides you things about, okay, I'm up to date, I'm out of date, and maybe I'm using min dependencies. It's not, as far as I know, it's not supporting indirect dependencies, only direct dependencies. And it's not really giving you a measure of how out of date you are. Another study we wanted to do is to find out to which extent are these different ecosystems supporting semantic versioning. So I hope I don't have to explain to you what semantic versioning is. So basically, well, semantic versioning, if you would use a caret constraint, then you are conforming semantic versioning because you assume that you can upgrade any minor or patch version. The problem is, one thing we want to compare is across different ecosystems, but the problem is there is not really a single unique way in which these different expressions here on the left-hand side, different constraints, are interpreted. Depending on the ecosystem, you might have a different interpretation. And so basically, semantic version combined might mean something different depending on which constraints you are using for which ecosystem. All of these in red are more restrictive than semantic versioning. All of these in green are more permissive than semantic versioning, and everything in white is semantic versioning. So based on this, we try to analyze for different ecosystems, are these different ecosystems increasing in semantic version compliance over time, and we saw that it was clearly the case for cargo. It's almost going to 100%, for NPM like 80% or so, and for packages. So that's actually a good sign. Ruby Gems is not supporting semantic versioning at all. The blue curve is much lower than. What we also found was that there's still a quite high percentage of restrictive to restrictive constraints, print constraints, which would actually be reduced to have more semantic version compliance. Then you have, of course, the notion of security vulnerabilities, so which effect of depending on components with no vulnerabilities is one of the top 9 application security risks by the FOSDEM Foundation. So there we did a small analysis to find out to which extent to quantify to which extent security vulnerabilities in packages may affect dependent packages. This was a smaller scale study because we didn't have access to lots of vulnerabilities. So only 399 vulnerabilities in 269 packages, but in total for the dependent packages this affected like 54%, 72,000 dependent packages. We wanted to know, like we did some survival analysis to find out how long does it take to discover a vulnerability. Basically, here you can see that after 2.5 years, 30 months, there's still 40% of the vulnerabilities that are not discovered. How long does it take to fix a vulnerability? Basically, after 1 year, there is still about 20% of vulnerabilities that are not fixed yet. How long does it take if you have a package that has a vulnerability that has been discovered and fixed? How long does it take before your dependents will actually also fix the vulnerability? Because maybe there is already a fix available in your package, but the dependent package is still depending on an older version that still has the vulnerability. That basically, okay, I could also show you the analysis, but just look at the blue curve. This is all the cases, the percentage of situations in which you have a dependent package to a package that has a known vulnerability that has been fixed, and in the dependency it's not yet fixed. In actually all the cases we studied, in 1 out of 3 packages, there was still a vulnerability available in the dependent package. So it's quite high, and this was actually surprising to us. Okay, why could this be the case? One simple reason could be that all of these dependent packages basically are not maintained anymore. There is no one to actually make the fix to fix the vulnerability. It could also, that's one of the reasons, the package is no longer maintained. It could be that basically you're simply using too restricted dependency constraints. Maybe it's too hard to upgrade to fix the problem. Maybe you cannot do it because of incompatible changes. Or maybe you're simply not aware there is any vulnerability because you're not using any security monitoring tool. So there can be many different reasons. This might be even a combination of all of them. So of course, so what we definitely need to do is use monitoring and update tools for monitoring and updating vulnerable dependencies. We already heard Bruce Hughes mentioned there's GitHub, there's Slick, there's for JavaScript reliable.js. Something reasonable. There's of course also the tooling that in the FOSDEM project is being developed, which could be used for this. And another one that's like similar to this that I heard about yesterday is that is very new to me is Eclipse Study, which is also a kind of combination of static and dynamic analysis for Java and Python, which is also promising a project that will be much more precise than just looking at package dependency data. To conclude, there is still a lot of work to do, and there is also quite a lot of challenges, especially like the thing that just mentioned before. If you want to detect vulnerabilities that really matter, how can we avoid false positives and false negatives? Really huge challenges with these transcript dependencies. How can we actually do this? The transcript dependency method becomes so huge that it's really a lot of resource consuming. We have to take into account semantic versioning, but semantic versioning is just a policy. You can follow it, but how can you be sure that you're actually following it? How can you detect whether a change is actually a breaking change? To do this, you have to do a like behavioral analysis, which is very difficult. It's actually undecidable in general. Okay, that's it.
Yes.
Very nice, interesting study. Did you find any particular package manager that does better than the others? Some ideas that you think others should follow?
Well, yes and no. So one of them that was clearly better than the others, I will go back to the beginning slides, was CRAN. But why is it better? Here, basically the green one is CRAN. It's always for everyone it's better than the others. But there's a specific reason for this. It's basically because it's using a rolling release policy, and actually you always have to rely on the latest version of all the packages you depend on. If not, then your package will automatically after a while be archived. So basically you're putting the burden of the dependency management on the dependence of the package, not on the package itself. This is actually like a good policy to have like at an ecosystem level, to have a good ecosystem in terms of all these metrics. Of course, it's much more effort for people that depend on the packages. So yeah, I don't know what's the best way. Should you put all the effort on the maintainer of a package or on the dependence of the package? These are actually two different sides of the coin. So CRAN is very good from that point of view, but it's actually, we also did a study for actually comparing what happens on CRAN compared to other packages, and actually lots of people are moving away from CRAN, and they are just saying there's too much effort here, I'm just going to put my package on GitHub, everyone who wants to use it, just download it and install it there from there, and I don't have to take into account all of these constraints because it's too much effort for me.
The dependency has breaks loose.
So actually they're just shifting the problem to somewhere else.
On the slide, we put like the list of like tools. So, yeah, like the GitHub, dependency management, Eclipse, this one. Do you know if they also got like indirect dependencies?
No, most of the tools, actually I'm not aware of any tools, maybe Eclipse Study is doing it, for taking into account transcript dependencies that is not this was at least not recently supported any of the tools. I think for this one it is supported to some extent, but this is brand new, so I cannot check this enough, not really. So I think that's the main limitation today. There is quite a lot of support and good support for direct dependencies. There's almost no support for indirect transitive dependencies. GitHub also. But it's only at, it's not at like a more fine-grained level where you do also static and dynamic analysis.
So like
That's already a very good starting
that kind of transitive dependency, like basically, if you don't have that kind of tool, how do you check it? How do you manage it? Because if you have like 10 dependencies that have 10 dependencies, it's like 2 hours for like a...
Yeah, of course. Yeah.
So
there's even a case, so we started exploring actually how, to the last question of the previous presentation, how can it actually happen that you have so many transitive dependencies? I mean, for many cases where in the beginning, at the moment you decide to start depending on a package, basically this package has zero other dependencies itself. So you say, okay, I'm going to depend on it, it's safe because I can manage it. Then after 1 year, you see that this package is starting to depend on others because of upgrades. And there were cases where we found that even without you knowing about it, suddenly after 1 year you have 5,000 transitive dependencies simply because you don't have control over what are your dependents doing with their upgrades.
do you have any advices to like some more control?
Also for these things you can actually have tools where you can say I want to limit my transitive dependencies, and you could have actually basically a tool that measures the amount of transitive dependencies, the transitive dependency depth you're facing, and have some warnings where you say, here watch out, you have either too many direct dependencies or too deep transitive dependencies.
Does that kind of tool exist?
Yes, I'm doing it. So for people that are interested, yes, we're building some tools called Open Source Toolkit. It's especially designed as an open source replacement for normally your white source or black duck, which are commercial tools that have these kind of capabilities. So one of the things that we identified as so this is clear, I'm not a compliance vendor at all. We're just a company that in the Latin space that had this problem at our company scale. So basically we have thousands of engineers that are experiencing this problem. So we decided to just fix it. It's not good, but it's possible. So we support 1 people